Hello, and welcome to part 4 of Ultra 10539's video series on how to get started with FTC programming. Today, we'll be writing an autonomous OpMode. This is a basic OpMode that will teach you how to use both an encoder and time-based drive for your pushbot. Let's first begin by adding an autonomous OpMode class to your OpModes folder. To do this, we can right-click on the OpModes folder, hover over New, click on a new Java class, and name it Autonomous OpMode. Then, like our teleop class, we can attribute this to the autonomous modifier that's available through the FTC provided SDK. To do this, we would type autonomous, and type new, and write auto. We could then extend our class to the FTC provided linear OpMode class. Linear OpMode is especially used for autonomous, so it allows us to linearly declare the functions that we want our robot to follow. We could then begin by declaring some of our class members, including our device map and movement variables. To do this, we can do device map robot is equal to new device map. Then we can also declare our elapsed time variable. Elapsed time is a great way to track the number of seconds that has passed in your autonomous OpMode. To this, we can do private elapsed time runtime is equal to new elapsed time. You can also see the device map comes up as red. This is because we have not imported the device map class. So we can right click on it, show context actions, and import the class into our class. After declaring our device map and our elapsed time variables, we can begin by creating some of the variables that we'll be needing for driving the robot. For these purposes, I'll be using variables that relate to the rev motors. So that includes static, final, double, counts, per motor rev is equal to 1440. We also have other variables, including the drive gear reduction and the wheel diameter inches. I'll be writing some of these out, and I'll see you then. Now that I'm back, you can see that I've written some of the important variables that we'll be needing, including the drive gear reduction, the amount of the diameter of our wheels, the counts per inches based on the diameter of our wheels, and the drive speed and the turn speed that we want to move at. Then we can begin by creating our encoder drive function. To do this, what we have to do is create a method called encoder drive. So it's a public void encoder drive, and we'll take in the following parameters: double speed, a double left inches, double right inches, and double timeout seconds. We can then, by creating two new variables, including int new left target and int new right target. And we want to ensure that the OpMode is still active, so what we will do is, if the OpMode is active, we will determine the new target position and pass that to the motor controller on our expansion hub. So to do this, we would do new left target, which is the variable that we just created, is equal to robot.leftFront get current position, which we will cast then to an int. Int is left inches times the counts per inch. We then have to do this for all four of our variables. Now that I'm back, you can see that I've created two new variables known as new left target 2 and new right target 2. These are to make up for the fact that we have bottom motors for left bottom and right bottom. You can also see that I've created we've attributed values to new left target 2, new right target 2, based on the motors that it will be working for. Then what we can do is turn on run to position on our motors. To do this, what we can do is robot.leftFront.setMode DC motor set run mode run to position. This will allow us to tell our motor to run to position. You'll also see that our DC motor class has not been imported, meaning that we have to right click on the DC motor, show context actions, and import the class. We can then do the same for each of our four motors. To do this, we can create a while loop. So we would do while our OpMode is active and the runtime of the seconds is greater than the timeout second that we want our encoder drive to run towards, and if the left drive and the right drive are not busy, Then we want our code to do something. And so I'll write that loop out and then I'll show you guys. Now that I've written the while loop out, you can see that I ask whether the OpMode is active. I check whether the runtime seconds is less than the amount of the timeout seconds that I have for the encoder derived value. Then I also check if all the motors are busy. So then we can open this while loop. We can begin writing our code. So we could first see the path that we want our robot to take. So telemetry.addData, which I introduced last video. We can do path 1. Then we can do some regex, so running to modulo 7d colon modulo 7d. And then we can attribute those modulo values to new left target and new right target. Our new left target and our new right target are the same as new left target 2 and new right target 2. That is why I will not be calling them. Then we can also get the current position of our left drive. Because our left front and left bottom are the same as our right front and our right bottom, we can also just use our left front and right front values. So telemetry.addData, path 2. We can then write the same code, so running to modulo 7d, comma, modulo 7d. We can then do robot.leftFront.getCurrentPosition. We can also do robot.rightFront.getCurrentPosition. And then we could also write a telemetry.update, which will allow us to see our see the telemetry on our driver stations in real time. Then we can begin by stopping the motion for our robot after the sequence is done. So robot.leftFront.setPower is equal to 0. And I'll do this for all 4 motors. You can see that I've written the set power 0 for all 4 motors, and now we can turn off the run to position on each of our motors as well. So to do this, robot.leftFront.setMode DC motor.runMode.run using encoder. And I'll do this for all 4 motors as well. You can see that I've begun to stop using our encoders, stop using run to position, and simply just use run using encoder for all of our motors. Now that we've written our encoder drive function, we can actually begin to write our actual autonomous functions. So we can write the override attribution to it, our function, and we can do public void run OpMode. You have to name it run OpMode as it extends from the linear OpMode FTC provided class. We can then do robot.init hardware map. We can also add some telemetry data to know that our robot has been initialized. So status resetting encoders. And we could do a telemetry.update so that our code will actually show up on our driver station telemetry side. We can then tell our motors to stop and reset all the encoders so the values are at 0 based on where your robot is starting from. So I'll write that out. Now that I've told the robot to actually stop and reset encoders once the code is run for the autonomous OpMode, we can then just write telemetry.addData, and we can see if the motors have actually been reset. So to do this, we can do path, we can do starting at modulo 7d colon modulo 7d, and similar to the idea that I implemented in encoder drive, our left front and our left bottom and our right front and our right bottom, both sides have the same exact values, so we can just use left front and right front to attribute both. So to do this, we do robot.leftFront.getCurrentPosition, and we can also do robot.rightFront.getCurrentPosition. And then we could write telemetry.update so the words actually come onto our driver station screen. Then we can wait for start, and then we can actually tell our robot to continue working. So now, once the driver hits play, it will actually begin to do all the functions that we want it to do. So now we can do encoder drive. We can do the drive speed number that we just used, so it will do at 0.6 at its power. It will go to 48, so it's 48 inches on both sides, and we'll do it at 5 seconds. We can then do another encoder drive, with it being the turn speed. And now, if you're working with motors, whatever side you want to turn to, say you want to turn to the left, your power for the right has to be the negative value of whatever you're turning on the left. So say you move 12 inches forward on the left, you would need to put negative 12 inches on the right, so that the robot would actually turn to the 12 inches to the left. So to do this, we would just do 12, negative 12, and 4 seconds. Then we can also do encoder drive speed, and now we can also just do reverse. So negative 24, negative 24, and 4.0. We can then write a sleep, which essentially just tells it to make sure that these all happen within a set amount of time, resetting everything and making sure that it all happens. And that's it. We've just written an autonomous OpMode. Congratulations on finishing this 4-part series on how to begin programming for FTC. Please feel free to email us at ultra@browning.edu if you have any questions or if any further concerns with our video. I will also link some of the important books that you can use when programming for FTC, including a book that is simply made for FTC that is called Learn Java for FTC. Thank you and have a good day, and I hope that these videos served useful towards your process in programming for FTC.